Today we're taking a look at section 5.1. We're going to be looking at addition of integers specifically. The section is addition and subtraction. And before we start with the manipulatives I just handed out, let's actually take a description for what integers are. So integers, your book uses the letter I. That is not traditional notation. There is no traditional notation. That didn't say it right. The traditional notation for integers is usually the letter Z. I is not so good because integers and irrational are both I's, so that's part of the reason why. Z comes from the Greek or Latin, I can't remember, for integers. We've done whole numbers now for quite a bit. Whole numbers start at 0 and increase 0, 1, 2, 3, 4. The integers start with the negative sides of all those values. So we're going to start with dot, dot, dot. We have -3, -2, -1. 0, 1, 2, 3, and we will continue on with the dot, dot, dot at the end. So your book's going to use an I. So our integers are positive and negative whole numbers. That's one sort of verbal description we sometimes say. And the first things that we're going to do are looking at different models for addition. And the first model for addition is the chips that you have. So if you take a look at your chips, they're dual-sided. Is that true? Mm-hmm. Yep. I thought that's the ones we ordered. We ordered them. Typically, when you order manipulatives, they'll have red on one side of things, or they'll use red for things. Red is going to mean negative numbers for us. Okay? That's a very typical approach for negatives, is to use red. Microsoft Excel uses red, right? In the red and the black. And the black means that you have positive money in your bank account, and then the red is bad. Negative money in your bank account, don't do that, okay? Now, the other side just depends on what the manipulatives are. So this manipulative set has used yellow. Black is more traditional, but it doesn't really matter. Reds are always the negative side. The other side, in our case, yellow, is going to be positive. Okay, everybody good with that? Okay, so we're going to look at a CHIPS model approach for addition to start with. So I'm going to use red and yellow since you have red and yellow for yours. Okay, and if we are looking at doing a chip model with addition, what we're going to do is we're going to draw a circle. It's sort of like the mat, you know, the playing area of the game or whatever you're doing, right? And what we're going to do is we're going to put inside of our mat 5 positive chips. So if you were to take your chips and you were to set them out, you would set out 5 yellow chips. Five yellow chips is in your mat. And then you're going to add into it 3 red chips because the red's negative and it says -3. So you've got your 3 red chips. Sorry, my chips don't all look the same size, but that's okay. Okay, everybody good so far? Okay, and then now we're going to introduce a concept called zero pairs. For those of you who've taken proportional and statistical reasoning, we talk about zero pairs in there as well. Works exactly the same way. If you have a positive and you have a negative, they add to 0. This is a zero pair, and it gets removed from your picture. So in a very real sense, on your manipulatives, you would take the positive, the yellow, and the red, the negative, and you'd remove them from your circle. If your fingernails will let you. Mine won't. They're hiding underneath the paper. Okay, no more. And then you do it again, right? So here's another set, and they'll get removed. And then I want to do it with my third set, and it gets removed. So when I'm done with the zero pair process, I should only be left with one color. It may be red. This one's not. It's yellow. But I'm only left with one color inside of my working area. In this case, I'm left with 2 yellows, and 2 yellows represent the number 2. There is nothing special about the red and the yellow. If you were doing your homework and all you had with you were a pink pen and a purple pen, use pink and purple and just tell me which one's positive and which one's negative. Write yourself a little key to the side, okay? Or if you only have a pencil, you can do one where it's hollow, you know, empty, and then one where it's shaded in dark, okay? And you just tell me which one's positive, which one's negative, and we'll be good with that, okay? So this is the chip model for addition. We'll use these manipulatives again for the chip model for subtraction when we come back next time. So if you want, go ahead and, that's the only one we're going to do. I know, it's not very exciting, but you want to take your chips and put them back in. So pass the chip bags around and we'll collect them. All right, I'm going to collect mine later. This isn't working. All right, so this one's a really nice model because it's super hands-on, right? Your kids are going to get to play with chips. It's also super cheap to do this because if you do not want to buy manipulatives, could you cut out little pieces of paper? Absolutely. You just need 2 colors of sheets of paper. Cheap, super cheap kind of stuff. It doesn't even have to be two-sided. These are nice that they are two-sided, but if things weren't two-sided, you'd just have a stack of red and a stack of yellow or whatever colors you'd use, right? Easy stuff. And it doesn't even have to be circles. They could be other shapes. Okay, so our next model is called the charged fields model. And it feels very much like the one we just did. It has this sort of effect of thinking about like positives and negatives in terms of charges, though. I think about batteries, stuff like that. So if that perspective resonates with the kids in your classroom better, they might like this one better, not from what it does, but just from the perspective of how it operates. So we still draw ourselves a circle as our playing field, our mat. And what we do inside the circle is that we put a positive inside the circle for every value that's positive. So we have +5, so we're going to put 5 positives in the circle, wherever you wish. And we have 3 negatives, so we're going to put 3 negatives inside the circle. And charges balance each other out. So a positive charge and a negative charge neutralize each other, right? That's a 0 pair is what we called it in the other model. So they'll neutralize one another, and we can group them together and remove them. We group it together, we remove. We group them together, and we remove. And what we're left with at the end is only one type of charge. In this case, ours is positive, but it could have been negative. And the answer is a +2 because I have 2 positive charges left. Is that good? Okay. The next one is called a number line model. The number line model is fabulous for drawing, but it's also fabulous for actually moving. So pretend you put along the floor like hopscotch tiles or something, right? I'm going to use the desks because they're set up so nicely already. And I start right here, and I'm supposed to be going 5 forward. I'll start over here at the wall, actually. The wall's 0. Okay, so I'm going to go 5 forward. I've got 1, 2, 3, 4, 5. And then the -3 tells me I'm going to go 3 backwards. 1, 2, 3. And the question is, how far am I from the wall from where I started? And the answer would be 2. So I can actually move along a grid on the floor. Kids can get up and move around, so your kinesthetic kiddos, this resonates very well. Visually, when we're drawing it, it works nicely too. So we can draw a number line. We can start at 0, and we can move forward 1, 2, 3, 4, 5. And then we can move backward 3. So 1, 2, 3 puts me here moving backward, and I'm left at the number 2. So this is the sort of the written down visual perspective of physically moving my body along a grid on the floor. Okay. We'll tell you that the last one is not my favorite. However, for your kids who struggle not struggle with patterns, but think in patterns, and that's just their mode of how they operate. So think about your kids maybe that have autism or Asperger's, those kinds of kids who think that way. The next one can be very useful as well. The next one's a pattern model. So what a pattern model does is a pattern model establishes the relationship based on prior knowledge. For example, I know what, and I'm going to start with something that we already have done back in whole numbers, 5 + 2, right? 5 + 2, we already did it before. We know what 5 + 2 is. 5 + 2 is 7, okay? My goal is to keep the first value, the positive one in this case. I want the positive one actually to be the same because I know what to do with positive numbers. And I want to change this until I get to the point in the pattern where I have a negative 3. And so the way it works is this. Say, okay, well, I know what 5 plus 2 is. It's 7. I also know what 5 plus 1 is. It's 6. And I know what 5 plus 0 is. It's 5. Okay, everybody good so far? All of that's whole number addition. We already would have known it. But what it does is it establishes a pattern of what comes next. So you'll notice that going down in this column, it's decreasing by 1 every time. Okay, well, I just keep doing that. Well, I decrease by 1 and I have negative 1. But over here, the same thing happens. It decreases by 1 every time too. Well, what comes after 5? It's a 4. Because I've established the pattern, not because I'm actually adding 5 and negative 1, right? Because the pattern suggests that that's the next value. And then I can do 5 plus negative 2 again, and the number that comes before 4 would be 3. And I can do 5 plus negative 3 again, and the number that becomes before 3 on the right-hand side is the number 2. So this is my 2 based on patterns instead. I think in terms of patterns, this is still not one that I like very much personally. Okay? Actually a really big fan of the number line model. That's my favorite. Okay. So we have time, I think, to talk about absolute values, and then we'll pick up with properties of integers on the video. I'll find the video that starts with that or give you portions of videos to start with that next time. But let's take a look at absolute values real quick before we end for today. Absolute value talks about what happens when we take positive and negative numbers and look at distances. So if x is positive, that's the first line on this, it says x is greater than or equal to 0, then the distance from x back to 0 is simply the value x. So the picture that we have here, if you want to think of it in terms of a number line, which I think is a good way to think of this, here's the number 0. These are values that are positive, right, on the right-hand side. So whatever this distance is, this is the absolute value. So in the first picture, whoops, this is my x, and this is my absolute value of x, and it's just whatever x is. It's just the distance back to 0. It's a positive number to start with, it stays positive. The other picture looks a little different, and it looks a little different because here we have 0, and here we have x, and this is still the distance of x, whatever it is, away, right? So this right here, the absolute value of x, and the absolute value of x ends up actually equaling negative x. And let me talk to you about why with a concrete example of a number. Let's pretend instead of this saying x, it said negative 5. What is the absolute value of negative 5? Well, what is the distance between negative 5 and 0? It's 5, right? But how do we express that my negative 5 changed to a positive 5? We express it by multiplying it by a negative value. And I know that feels sort of funny, but we express that negative 5 changing by putting another negative in front of it. It doesn't make it negative, it makes it positive. So even though it looks like now I have a negative number, I do not. I have only the positive number, because I had a negative number to start with, and a negative times a negative is a positive. Okay, this is how absolute values are always defined. It just feels funny. So we're going to look at some questions related to absolute value, and then we'll pause for today. Do keep in mind that we have 3 types of numbers that we're working with in reality. We have positive numbers, we have negative numbers, and we have what? 0. 0 is not positive, and 0 is not negative. So as we think about these questions, the number 0 will often come in as an example or a counterexample that does funny things. So keep the number 0 at the forefront of your mind as you're looking at absolute value problems. So example 5 wants us to just decide if something's either true or false. And if it is false, it wants us to show an example of why it's false. Okay? So if it's true, we kind of get off scot-free. We don't have to justify or anything with these particular directions, although we'll talk about why. But if it's false, we have to show an example that makes it false. So the first one says that the absolute value of x to the fourth is equal to x to the fourth. Is that true or is that false? What do you think?
True.
It's true. Yeah, this is a true statement. As you're trying to decide, one thing to decide is, are the number values going to be the same? Ignore the signs for the moment. Is x to the fourth equal to x to the fourth? Well, yeah. If I take a number and raise it to the power of 4, it's the same as itself. So the real concern here is whether or not the signs stay the same. On the left-hand side, it's an absolute value, so this side is definitely positive, right? Is this side also always positive? It is, and it is because the power is what? Even. So this one is automatically positive as well. So this is a true statement. How about part B? That one's false. But if we say false, we have to give an example why. So by example, I mean we have to give a value for x. X equals what? What would be an example that makes this show up to be a false statement? -2 will work, sure. Okay, so let's try -2. So if I take -2 and raise it to the power of 5 on the left and then absolute value it, and I take -2 and raise it to the power of 5 on the right. On the left, I'm going to get, they're both going to be 2 to the 5th, which is 32, right? But on the left, it's going to be positive. How come? It's not because it's odd. It's because it's in absolute values. Because it's in absolute values, the absolute values are going to make it be a positive number. But because it's odd, like Deborah noticed, it'll actually end up staying negative on the right. Because I have 5 negative values, and an odd number of negatives is still negative. Okay? So these two values, it's positive on the left, it's negative on the right, it doesn't work. And in fact, our example could have been any negative number, and it would have failed. So lots of options. How about C? The absolute value of x is not negative. What do you think? That is true. Now, D is almost the same statement. The absolute value of x is positive. It is false. So if C is true and D is false, what gives? 0 gives. The absolute value of 0 is 0. And that's not positive. But it's not negative, right? It doesn't work for the other piece, right? That's why part C is okay, right? This is going to be positive or 0. And positive and 0 are not negative, so it works. But 0 is not a positive number. It's a neither number. So it fails to work for part D.